So, I was discussing in last class that we will measure some parameter and then how to report the result. So, that basically if measured parameter is x, then we report as a x equal to x best plus minus delta x. Okay. So, delta x is basically error in the measurement, as I told this what are the factors determine this delta x, that we will discuss later on. But this x best, it is controlled, it is the x best basically you will calculate the value of x. Now, that you are writing in this format. Now, x best, what will be the significant figure of this x best, that will depend on this delta x. Okay. Now, you have to know the significant figures, what is significant figures. Okay. So, that I have discussed, and now you are able to write your result in a proper format. Okay. So, then always we will try to understand, we try to get confidence on our result. For that we compare our result with in different ways. One way is, as I told, if standard value or true value is available, true value of this parameter is available, then we compare with this x best, we compare with this true value. Okay. So, if it is close to this true value, so then this is fine, your result is quite good, we are very happy. Okay. So, this way we compare, but if true value is not available for some parameter, then second way we try to get confidence, that we compare with this result with other experimental result. Somebody has done this measurement and reported the result. So, that is example I gave you, that if you measure this resistance of a resistor and find out this value basically say 15 plus minus 1 ohm, okay, 1 ohm, and your friend have measured the resistance of the same resistors, and he found that 25 plus minus 2 ohm. Okay. So, obviously, so how to compare? So, we take the difference between these two values. So, this difference is basically 25 minus 15 equal to 10 ohm. Okay. So, this 10 ohm is not within the range of error 2 ohm or 1 ohm. So, definitely it is your result is whether correct or not. So, you cannot tell confidently. Okay. So, something wrong in your measurement or your friend's measurement. Okay. So, one may be correct, another may be wrong, or both may be wrong. Okay. So, to find out that one, again you have to repeat the measurement and compare it. Okay. So, this way we compare our experimental result to get confidence, to conclude that no our result whatever I got, this is very very good result. Although it, as I told, this all the time this error will be there, but that should be estimated, and that is the delta x that we will discuss later. Second point is that this you got some you are measuring some say or you are doing some experiment to verify the some law, okay, to verify some law. Okay. So, suppose you are studying the momentum conservation of in the isolated system. Okay. So, in that case it is the you have, so you have to measure the so momentum conservation. Okay. In this type of experiment you are basically verifying the momentum conservation. So, what does it mean? The initial total momentum of the initial momentum of the system should be equal to initial total initial momentum should be equal to total final momentum of the system. So, from momentum conservation, this is the condition that is available with you. Okay. Now, for this experiment you are you have measured, first you have measured the initial momentum. So, that is say P, initial momentum P equal to some value you got 1.49 plus minus 0.03. Okay. And then final momentum you got say Q, that is 1.56 plus minus 0.06 say this is the. So, now you see this, definitely these two values are different. Now, whether you will conclude that momentum is not conserved or your measurement is wrong. So, how to decide? So, that means how to get confidence on your result. So, how to do that? So, that is what I am discussing. So, in this case then generally we take the help of just we plot the difference with or we I think we in this case we will not plot difference because this is one measurement. Later on I will show also we plot difference. So, in this case what we will do? In this case I will do this, I will just take a graph paper, and then I will scale it, say this is 1.4, this is 1.5, okay, because my value, initial value, what value we got? P equal to initial momentum 1.49 plus minus 0.03 and final momentum Q equal to 1.56 plus minus 0.06, okay, 0.06. So, now I will basically plot it. So, its range is 1.4 to 1.6. So, I will take a scale and then if you plot. So, here what is this 1.49. So, it is close to 1.49, it is close to 1.5. So, this value basically I can plot this value, say it is and plus minus 0.3 plus minus 0.3. So, I can this is the point 1.49 and then some error bar on this uncertainty error bar 0.3, say this is the plus minus, okay. And then another one is 1.56, 1.5. So, this is 1.55 So, it will be slightly higher than this 1.55 and plus minus 0.6. So, double of it. So, this each one is 0.05. So, that means this error bar will be this 0.6 plus 0.6 minus 0.6. Okay, this is the error. Okay. Now, here you have to see that if these two results are overlapping, then it's a accepted result, is a good result. Okay. So, accepted result we can say. So, there is a overlapping in this region, there is overlapping in this region, okay, of these two. So, if you plot and this find out that there is overlapping of these two results, then we tell this is the accepted result, it is the good result. Okay. So, this way we compare the result. Now, you see momentum you are measuring of a system, momentum you are measuring of a isolated system to check the verify the conservation of momentum. So, this whatever this data you got, this one set of data, you can repeat the measurement, you can get another sets of data. Okay. So, another sets of data you are getting, say p equal to 3.10 plus minus 0.03, okay, 0.03, and q we are getting 3.12 plus minus 0.06. Okay. This is another set of data okay, from the same system. So, because here this you can because this initial momentum, so it depends on the initial velocity, you know. So, that may be during different measurement, means if you are repeating the measurement, you cannot keep, may not be able to keep the velocity same, although mass same. If you take two ball, one ball is one ball and there is another ball. So, they have initial velocity. So, they have initial momentum, okay, total momentum that is a p, and now there is a collision between these two, and then after collision there is a elastic collision, of course, there is a velocity of these two ball will be different. Okay. So, so this velocity, although mass of these two ball are remain same in each experiment, but their velocity you cannot control, it can be arbitrary. Okay. So, that is why these values p value for this is 1.49, this can be 3.10, and this again if you repeat this experiment, then third set of data you will get say 2.16 plus minus 0.03 and q equal to 2.05 plus minus 0.06. Okay. So, these three sets of data you have taken. Okay. Now, as I told that you cannot control the velocity, all the mass are same. So, momentum will be different, and this magnitude wise it a huge difference. So, so our aim is to just compare just between these two, because we know these two should be the same. Now, here three sets of data. Now, conservation of momentum, whether this one is followed, this one is verifying in better way, or this one or this one. Okay. So, if in this situation how to compare this result, okay, how to compare this result to get confidence that okay, our measurements all are very good, or one of them is not correct. So, how to compare? So, in this case we plot the difference. Okay. We plot the difference. So, here difference is how much? This is 0.07 difference between these two. and what will be the plus minus. So, generally later on I will show you that this error of individual one for final this when for final error. So, these are additive, we have to add them. Okay. So, this error we take 0. Error range we take 0.09. Okay. And in this case it is the 0.02 this difference. In this case plus minus again this for all cases it is 0.09. In this case it is 0.11 and this plus minus 0.09. Okay. So, we find out this difference and we plot it, difference we plot it. So, if difference is 0, if this difference is 0, so this is the best result, there is no question. So, if difference is 0, so it is the best result, but in our cases difference are not 0, but what is the difference, what is how big this difference. So, that to, and in each case to compare that one, if you plot this discrepancy or difference. So, in first cases so this is 0.1, then I can write this one I think yeah I should take this one is a 0.1, 0.2 minus 0.1 minus 0.2, 0.2, and we have taken basically q minus p. So, these are basically q minus p we have taken. So, here we are plotting basically q minus p difference with error bar we will plot. So, here 0.7, 0.7 means somewhere here point, okay, and then plus minus 0.9 means 0.1 plus minus. So, 0.9, so almost I think this is 0.7. So, 0.2, this is my point. Okay. So, for second one this is 0.2, different 0.2, here 0.2 and then plus minus 0.9. So, its length will be same for all. Okay. And then this is 0.11. So, this 0.11 is close to here, and then I have to 11.9, I think it is closely. Okay. So, how good your these three measurement to compare it, if I if you plot this difference, it's if it is 0, it is the absolute result, excellent result, but that never happens. But now, if you compare this and then you can tell this there is a overlapping among this difference. It is not that here one result is here, another we are getting like this. Okay. Then we have to, this result will not be accepted, this something wrong in this measurement. So, we have to discard this data. So, but in this case is nicely overlapping among this. So, overlapping region you can say this to overlapping region is this. Okay. So, there is a overlapping among these three results, then this result we tell this is accepted, all measurements are accepted and results are good. Okay. So, this way we compare our results, just we will measure and just report the results following the significant figure and this error plus minus delta x, that is not enough. So, you have to try to get confidence on and measure how confidently we will tell that our result is very good, our measurement is perfect. So, for this these are the ways to conclude it, okay, to tell your result very confidently. Okay. So, next example I can tell that this also we check our result, okay, using the graph. So, how to check your result, or how to get confidence on a result. So, there are different ways to check it, and for one experiment all checking is not possible. So, for different experiment, different situations, and for different situations different ways are there, and that is what I am discussing. So, sometimes we check the result using the graph, in which cases, say Ohm's law, you are verifying Ohm's law, right. So, V equal to IR. Okay. So, basically you are varying I and measuring V, right. You know how to measure the Ohm's law, right, and you know this is a linear relation between V and I, and if you get your result, theoretically you can tell that there should be this relation can be represented like this. So, it will be straight line passing through the 0, right. So, this is in your hand, okay. This is the standard one. Now, you got the data, means current versus voltage. So, 1, 2, 3 whatever this, say 2, yes. So, I think 2, 4, 6 etcetera, etcetera. Okay. Okay. So, this data to check that your data, your experiment is correct or not. Okay. So, what we will do? We will plot this data, and we will see whether this data is presenting, can be represented by a straight line which should pass through the 0. If so, then I will tell, okay, my experiment is very correct. So, this is the another way to check your result using the graph. Similarly, say Ohm's law, and then this another is Hooke's law. Hooke's law. Okay. Hooke's law, what is this? This stress and strains are linearly related, right. Like if you take spring, okay, extension of spring, so that force is proportional to the extension. So, this proportionality constant we write K x. Okay. So, K is basically we tell spring constant. So, F equal to, so you are applying force to extend it and measuring the extension for different force, different extension. Now, this is again between force and this extension linear relation. Okay. This is a standard relation, it is telling theoretically this expression is telling it should be linear. So, now if you do the measurement applying different force or for different extension, what is the force? Okay. So, you have data. Now, you check how good your data or how good your experiment, just plot it and see whether you are getting this linear fitting or not. So, just plot and check it. Okay. So, on the average it is linear. So, you are confident now that your experiment is correct. So, this is the way we check our result using the graph, depending which way you will check. So, that will depend on the on the situation, means what are the things in your hand. So, with which you can compare your result, your experiment. Okay. So, this way one can check the result to get the confidence. Okay. So, next I will discuss about the slightly furthermore. So, whatever error I have written, this x equal to x best plus minus delta x. Okay. So, as I told, this delta x is called the absolute error, Okay. And then another error, that is delta x by x. If we represent this way, then we tell this is the relative error, Okay. Also, if you delta x by x into 100, then we tell is the percentage error. Okay. Is the percentage error, in percentage error. Okay. So, and this relative error, whatever we are telling, this also we tell the fractional error, Okay. So, your error you can express by absolute error, you can express by fractional error, you can express by percentage error. Okay. But generally we find out the convenient way to express the error for all result. For all result, for all experiment, generally we do not write in absolute error, we write in fraction error or percentage error. So, that depends on the situation and how comfortably we can represent our result. So, depending on that, one of them we use. So, if you measure a length L, right, length L, that is say 50 plus minus 1 centimeter. Okay. So, this way we write, but other way also we write, we can write this. So, what is the in percentage error also we can write. So, what is the relative error then here? In this case your delta L by L. So, that is delta L is 1 and L is 50. So, this basically 0.02. Okay. So, this will be the relative error. Okay. So, but your result you can tell this is a relative error, but to express your result you cannot use this directly. So, to express this your length with error. So, generally if you take this percentage error from here. So, this percentage error is so you have to multiply it with 100. So, delta L by L into 100. So, that is basically here you will get 2%. Okay. So, then you can result your result this length L equal to 50 plus minus 2%. Okay. You can write 50 centimeter, here generally we write this way 50 plus minus 1 centimeter. So, also you can express your result 50 centimeter plus minus 2%. 2% means 2% of 50 centimeter. Okay. So, 2% of 50 centimeter how much into 2 by 100 2 equal to 1 centimeter, that is what. Yeah. So, we express in terms of percentage error, also we can express in absolute error. So, this way we present our final result, and now next question is coming, that as I told this, how to find out the delta x, how to find out the delta x, that is what we need to discuss. And yes, and what are the origin of this delta x. Okay. So, for this basically you have to we have to know the different source of error, different what are the types of error. Okay. So, types of error in general we can classify types of error. I think I will discuss in next class this what are the types of error. So, here I will stop it. Thank you for your attention. Yes.